The deep dive is open. All right, let's jump right in. For, gosh, almost 100 years now, physicists have been chasing this ultimate prize, right? The theory of everything.
The Holy Grail, yeah. A single description of reality.
Exactly. Something that makes sense of, the tiniest quantum fuzziness and the huge sweep of the cosmos, gravity and all that.
And it's been incredibly tough.
Yeah, why is that? Why has this been such a roadblock for nearly a century? I mean, we know it boils down to that clash, right?
It really does. You've got Einstein's general relativity, beautiful, describes gravity as smooth space-time geometry.
Classical geometry.
Classical continuous. And then you've got quantum mechanics, totally different beast. It's all discrete packets, probabilities, fundamentally informational.
And we try to smash them together like in a black hole or the Big Bang.
The math falls apart. Catastrophically sometimes. Because you can't just, paint quantum effects onto a classical background and call it a day.
Okay, so that's the setup. What we're diving into today, though, sounds like a completely different approach. This quantum-unified vacuum idea, the Qmn theory.
Precisely. It's a paradigm shift. Instead of trying to force GR and QM together, this theory proposes that gravity itself actually emerges from quantum information.
Whoa, okay, so gravity isn't fundamental in the old sense. It's quantum information doing the driving.
That's the core idea we're exploring. The Q theory offers a way, mathematically rigorous and crucially testable, to modify Einstein's field equations. It puts quantum entanglement right there as a source of gravity.
Okay, show us the equation. What does that look like? So the modified equation, the heart of this whole thing, is Gₘₙ plus lambda Gₘₙ equals 8p over c to the fourth times the sum of Tₘₙ plus this new term, Qμ entanglement. Got it. Gₘₙ is space-time curvature. Lambda Gₘₙ is the cosmological constant part. That's the geometry side.
Standard stuff, yeah.
But on the right, the source side, it's not just Tₘₙ, matter and energy stress.
Right.
It's Tₘₙ plus this Qμ term, this entanglement tensor. So entanglement itself is warping space-time.
That's exactly the thesis. Curvature isn't just from mass and energy, it's also from how quantum information is organized, how it changes, how it's entangled across the vacuum. This single framework is what we're arguing is the most solid candidate yet for that theory of everything.
All right, let's dig into that Qμ tensor then. You said it's not just pulled out of thin air. It's built from, what, 3 core physical concepts?
That's right. 3 pillars representing the fundamental ways quantum information has to manifest geometrically for gravity to emerge. It's derived, not just added.
Okay, pillar number 1.
The first is what we call the curvature thermal coupling. It's the alpha term. Mathematically, it looks like alpha times Rₘ T minus 1/2 Gₘₙ RT.
Okay, Rₘ is the Ricci curvature, tells you how space-time is bending. Gₘₙ is the metric. R is the scalar curvature. But T temperature.
Yeah, and this immediately makes you think of thermodynamic gravity, like Jacobson's work.
Exactly. Is gravity just heat? What's the T here?
Yeah, it's not everyday temperature. It's the Unruh temperature. You remember the Unruh effect? An accelerating observer sees the vacuum heat up, detects thermal radiation.
Right. Acceleration creates a sort of perceived temperature from the vacuum fluctuations.
Precisely. So the alpha term formalizes a direct link. It's a space-time curvature itself is coupled to this local Unruh temperature, Tx.
Hold on. So the bendier space-time is the hotter the quantum vacuum appears locally, and that heat feeds back into the gravity equation.
You got it. The Unruh temperature, Txx, is proportional to the square root of R⁻ₛ v mu v nu, essentially tied to the local acceleration or curvature. Spacetime feels this heat. It's a physical mechanism connecting macroscopic quantum effects, like Unruh radiation, directly to the metric. Thermodynamics driving geometry. That's the first link.
Okay, that's a fundamental shift. Right. Pillar number 2. You mentioned entropy gradient. Yes, the entropy gradient stress, this is the beta term. Beta times Kb, the Boltzmann constant, times, parenthesis, nabla mu s, nabla nu s, minus 1/2 Gₘₙ times nabla s squared.
Okay, S is entanglement entropy. So nabla S is the gradient, how entanglement changes across space. You're saying the change in entanglement acts like stress or pressure.
Exactly. Think of it as the kinetic energy of entanglement. Where entanglement is changing rapidly, that gradient creates a stress energy contribution. Older entropic gravity ideas had trouble making this fully relativistic.
Right.
Here, the gradient is baked right into the field equations as a proper tensor source. It's like pressure waves in the underlying quantum information field.
And this is the bit that potentially explains away dark matter, right? The pull comes from information gradients, not invisible particles.
That's its big role on cosmic scales, yeah.
Yeah.
We'll definitely circle back to that, is how gravity arises from information organization.
Okay, what's the third pillar? The most quantum-y one. That would be the quantum fluctuation stress, the gamma term. It's gamma times sigma mu sigma nu minus 1/2 g mu nu sigma alpha.
Sigma mu.
Yeah.
What's that representing? You said qubit interactions?
Yeah, think of sigma mu as representing the sort of collective background jiggle, the continuum limit of how fundamental quantum bits, maybe on some pre-geometric network, are interacting. Even in empty space, there's this irreducible quantum noise.
So if the vacuum is like a fabric, alpha is how it heats when bent, beta is tension from entanglement differences, gamma is the inherent fuzziness, the pixelation.
That's a good analogy. It's the stress coming from the fact that reality might be discrete at the bottom, built on qubits or spin networks or something. This gamma term connects the smooth geometry we see to that underlying discrete, noisy quantum reality. It ensures the model is truly rooted in quantum information. Without it, you lose that direct link. Okay, 3 pillars: thermal coupling, entropy gradient, quantum fluctuation. But adding stuff to Einstein's equations, that's dangerous ground. What about conservation of energy and momentum? Does this whole thing break physics? That's where the elegance comes in. You know, general relativity is built on the Bianchi identities. These geometric rules guarantee that the Einstein tensor, Qμ-nu, is automatically conserved. Its divergence is 0. Nabla mu Qμ-nu equals 0.
Right, and in standard GR, that forces the matter side, Qμ-nu, to also be conserved. Energy and momentum are safe.
Exactly. Now, in our modified equation, the Bianchi identities still hold. We haven't changed the geometric side structure, so Qμ-nu is still divergence-free.
Meaning the entire right-hand side must also be divergence-free.
Precisely. The divergence of the total stress energy, Tμ-nu plus Qμ-nu, must be 0. Nabla mu of Tμ-nu plus Qμ-nu equals 0.
Wait a minute, so the theory doesn't assume entanglement energy is conserved. The geometry forces it to be conserved.
Yes, that's the beauty of it. The conservation of the entanglement energy momentum tensor, Nabla mu Qμ-nu equals 0, isn't an extra rule we added. It's an unavoidable consequence of modifying the source term within the existing geometric framework of GR. If Qμ-nu wasn't conserved, the whole theory would be mathematically inconsistent. It's built in. Okay, that's reassuringly solid, mathematically. Now, let's get to maybe the wildest claim, deriving fundamental constants, like the numbers that define physics, from geometry. How does that even work? This comes from something called the fractal holographic principle. The idea is that the universe, at its deepest level, isn't smooth continuum. It's an information structure that's self-similar, like a fractal.
A fractal universe.
At the informational level, yes. And the fundamental constants we measure, like the strength of electromagnetism, aren't arbitrary numbers. They're basically scaling factors inherent in the geometry of this underlying fractal vacuum.
Okay. So there's a specific geometry you're talking about. There is. The theory introduces a key value, the fractal dimension of spacetime, d sub f or df. It's derived from how information flows in this emergent structure. The value is df equals log 8 over log 3, which is about 1.8928 log 8 over log 3. Why those numbers? Is this numerology?
It sounds like it at first, I know, but it's tied to the holographic idea how you encode a 3D volume's information on a 2D surface. The theory argues the fundamental unit involves 3 qubits, giving 8 states. 2 cubed is 8. This dVef reflects how information density scales as you go from the boundary to the bulk in a way that produces our familiar dimensions. It's the dimension of the information substrate itself.
So it's a specific value needed for the quantum network to correctly generate our 3+1 dimensional spacetime. That's the claim. And here's the kicker. This dF value is then used to geometrically derive the fine structure constant, alpha EM, the number that governs electromagnetism. You derive alpha, like 1 over 137?
Approximately 1 over 137.036, yeah. The derivation connects alpha EM directly to this fractal dimension dF.
Okay, deriving one constant is amazing, but physicists always worry about fitting things after the fact.
Right.
How do you show this isn't just a coincidence? A clever math trick.
Because it's not just one constant in isolation. It's part of a network. Remember the gamma term, the quantum fluctuation stress.
Yeah.
The theory also derives the value of that coupling constant, gamma, using both the fractal dimension dF and the derived fine structure constant, alpha EM. The formula is gamma equals h bar times alpha EM over 2 pi e cubed dF, and the value comes out around 7.297 times 10 to the minus 3.
Which is numerically very close to alpha EM itself.
Almost identical. suggesting the quantum vacuum's intrinsic noise level, gamma, is fundamentally tied to the strength of electricity and magnetism, alpha EM, linked by the universe's fractal geometry, dF. If it were just numerology, getting this second constant related to a different physical process to also line up via the same geometry would be, well, an unbelievable coincidence. It points towards unification.
Okay. That's compelling. But earlier we talked about this Qμ term needing to fade away on large scales. Otherwise, quantum gravity would be obvious everywhere. You mentioned a scale-dependent coupling.
Exactly. This is crucial for the theory to actually match reality. The coupling constant alpha, the one in the first pillar, the thermal coupling, it can't be just a fixed number.
Because then the quantum effects would dominate gravity all the time, which they clearly don't in, say, the solar system.
Right. So alpha has to depend on scale. We write it as alpha z. It depends on wave number k and redshift z.
Remind us what HAPE means here, conceptually.
K is basically the inverse of the length scale. High K means tiny distances, high energies, think near black holes, particle collisions. Low K means vast distances, cosmological scales, galaxy clusters, universe expansion.
So alpha K and Z needs to be strong at high K and weak at low K.
Precisely. The specific form proposed is something like alpha K of Z equals some base value alpha divided by 1 plus K over K star of Z squared. K star is some characteristic scale which might evolve with redshift cis. So when K is small, large scales, that K over K star term is small. The denominator is close to 1, but wait, no, the other one. K is small, K over K star is small, denominator is near 1. Oh, see, the formula was alpha times 1 plus K, K2 inverse. Okay, right, inverse, sorry, should have been clearer. So when K is small, KK is small, the term in brackets is close to 1, so alpha K, KZ is close to alpha. No, wait, let me reread that. Alpha 1 plus KZ, okay. If K is small, large scales, KK is small, the denominator is near 1, so alpha KSE is close to the full value alpha. If K is large, small scales. No, that doesn't seem right for making it negligible at large scales. Let me check the outline. Ah, I see. The correction itself might be suppressed at low K, or the coupling might change. Let's rethink this.
Okay, the outline says negligible recovering standard GR at low large scales, but becomes active at high energies or small scales. So alpha needs to be small at low K, large scales, and large at high K, so small scales.
Right. My apologies. The effect of the term needs to vanish at large scales. The coupling function alpha kz alpha 1 plus ktgz does mean alpha gets smaller as k gets larger. So how does it become negligible at large scales, small k? Maybe the terms it multiplies become small at low k, or maybe the alpha itself relates to something that's only significant at high curvatures. Let's stick with the core idea for now. The theory needs a mechanism, likely involving this alpha k, to ensure the quantum correction is strong where needed, small scale shy energy, and weak where GR works fine, large scales low energy. Yes, that's the critical point. The scale dependence, possibly tied to K and Z, is the bridge. It allows Qμ to provide the needed quantum gravity effects near singularities or in the early universe, while effectively disappearing for planets and stars, recovering GR. That's how it unifies the micro and macro worlds.
Okay, so assuming this mechanism works, let's put the theory to the test.
Yeah.
The big cosmological headaches. Hubble tension, dark matter, dark energy, black hole singularities. Can Qμ really tackle all of them?
That's the claim. And the solutions aren't separate fixes. They should emerge naturally from the properties of this single Qμ tensor, especially its scale dependence.
Let's start with the Hubble tension. Big problem right now. Early universe measurements from the CMB give one expansion rate, H0, but local late universe measurements give a significantly different, faster rate.
And the error bars don't overlap. It suggests the standard model, lambda CDM, is missing something fundamental about cosmic expansion.
So how does Qμ fix it? You mentioned that scale-dependent coupling, alpha casters.
That's the key. The Qμ tensor via this scale dependence subtly changes the expansion history. Specifically, it tends to suppress the growth of large-scale structures, galaxy clusters and the like, primarily at late cosmic times, say for redshift Z less than 2.
Okay, why does slowing down structure growth late in the universe change the measured H0 value?
Because the local measurements rely on a distance ladder calibrated using standard candles, whose distances are inferred based on the standard expansion model. If Qμ alters that late-time expansion and structure growth, even slightly, it changes the inferred distances.
It's like the cosmic rulers themselves are slightly different than we assumed in the recent past.
Exactly. The suppression of large-scale growth, low k, acts like a gentle brake, changing the distance-redshift relation just enough at low redshifts. When you factor this Qμ effect into the model,
Well, A0 do you get?
the prediction comes out around H0 a 68.2 kilometers MPC.
Okay, that's right in line with the large-scale structure measurements, like from DSI recently. And it leaves the early universe CMB physics untouched.
That's the crucial part. It resolves the late-time tension without messing up the beautiful fit we have for the CMB acoustic peaks from the early universe. It's changing gravity itself, not questioning the measurements.
All right, one down. What about the elephant in the room, dark matter? If Qμ explains it, how? Which part of the tensor does the work? That falls mainly to the beta term, the entropy gradient stress. Remember, that term is driven by the gradient of entanglement entropy, nabla S.
So where entanglement changes across space, you get cavity.
You get an effective acceleration, yes. The non-uniform distribution of quantum entanglement in and around a galaxy creates a stress energy source that generates an additional gravitational pull, precisely mimicking what we attribute to a dark matter halo. It's an emergent entropic acceleration.
This sounds a lot like MOND, modified Newtonian dynamics. MOND also explains galaxy rotation without dark matter by changing gravity's rules. It produces similar effects, yes, MOND-like phenomenology, but the origin is completely different. MOND is, let's be honest, an empirical fit, a modification of Newton's law that works well but lacks a solid theoretical relativistic foundation.
Whereas
Qμ provides this effect from a fully relativistic covariant theory, derived from first principles of quantum information and geometry. The acceleration isn't tuned by hand, it emerges from the conserved stress energy tensor Qμ.
Is there a smoking gun? A specific prediction that ties this entropic gravity directly to the visible matter we can see? Yes, the baryonic Tully-Fisher relation, or BTFR. This is a remarkably tight observed correlation. A galaxy's rotation speed is locked to its visible baryonic mass, stars and gas, by a simple power law. V rotational to the fourth power is proportional to m baryonic. And standard dark matter models struggle to explain why that relationship is so tight and universal.
They often require some fine-tuning of the halo properties. But in the Qμ picture, the extra gravity is caused by the entanglement gradients, which are themselves tied to the distribution of the visible matter that anchors the entanglement. So the BTFR scaling should emerge naturally. Fits to galaxy rotation curves, like from the SPARC database, are predicted to be better with this entropic model than standard halos.
So the dark gravitational effects are just geometry responding to the information patterns laid down by the normal matter.
Okay. Well, what about dark energy then, the accelerating expansion?
Here, Qμ reframes the cosmological constant lambda. Instead of being this mysterious static vacuum energy with a value that's absurdly fine-tuned.
The worst prediction in physics problem. Right. Instead, lambda is seen as a dynamic, thermodynamic quantity. It's related to the overall entanglement entropy of the observable universe. As the universe expands and entropy grows, this effective lambda can evolve, driving acceleration without needing a fixed, unnatural vacuum energy density. So, dynamic dark energy linked to entropy. Okay, final hurdle, black holes. GR predicts singularities, infinite density, and the information paradox. Where does information go? What does Qμ do at the brink? As matter collapses and curvature skyrockets towards the Planck-scale, the Qμ corrections become dominant. Specifically, the gamma term, the quantum fluctuation stress, kicks in strongly.
And it acts repulsively.
Effectively, yes. It provides a quantum pressure, a resistance from the vacuum structure itself that halts the collapse before infinite density is reached. No singularity forms.
So collapse stops, but what's left? Does it still evaporate? It still radiates energy, likely similar to Hawking radiation, but because there was no true singularity and arguably no true event horizon in the classical sense, information isn't destroyed. The evaporation continues until it reaches a stable endpoint. A non-singular black hole remnant, or BHR. A stable remnant. Does the theory predict its mass?
It does, and it ties back to that fractal geometry. The remnant mass is predicted to be the Planck mass divided by the square root of the fractal dimension df. So remnant equals m Planck over square root of df. Numerically, that's about 0.726 times the Planck mass.
Tiny but not zero, and stable.
Yeah.
Could these be dark matter candidates themselves?
They are definitely proposed as such. It provides a concrete endpoint for collapse, resolves the information paradox, and potentially explains dark matter via these primordial remnants. It shows the theory holds together even in the most extreme quantum gravity regime.
Okay, the consistency is impressive. It ties up a lot of loose ends. But theory is one thing. You said it's testable. How are people actually trying to prove or disprove Qμ right now?
The strategy has to be multi-pronged. You need tests across vastly different scales in the lab, in deep space, and using cosmological data.
Let's start small scale. Lab tests.
One key experiment is LUXE at d ease y. It's designed to push electrons through incredibly intense laser fields, essentially accelerating them violently, to look for the Unruh effect that thermal radiation predicted for accelerating observers.
But the Unruh effect is supposed to be incredibly weak, right? Almost impossible to detect normally.
Normally, yes. But remember the alpha term, the curvature thermal coupling in Qμ. It predicts that the intense energy density of the laser field enhances this coupling. The prediction is that the ratio of Unruh photons to background Compton scattering photons should be boosted by maybe 2 orders of magnitude 100 times compared to standard predictions.
Okay, that sounds potentially detectable. So if LUXE sees thermal photon, but only at the standard predicted low rate,
then the Qμ alpha term mechanism is wrong, or at least incomplete. Finding that significant enhancement with the right thermal spectrum would be huge evidence.
what else in the lab? Interferometry.
Yes, quantum interferometry with large molecules. You send these massive quantum objects through beam splitters and look for tiny phase shifts when they recombine. Qμ predicts a new source of phase shift.
How does that work? The formula for the phase shift, delta phi, gets an extra term. Delta phi equals the standard quantum shift plus something like eta times gm squared over h bar c times alpha times delta s. Delta S, the difference in entanglement entropy between the two paths the molecule could take.
Exactly. If you can manipulate the entanglement environment along the paths and measure a phase shift that depends on that entanglement difference, delta S, and scales with the coupling alpha, you've essentially seen entanglement directly affecting a particle's trajectory in a way predicted only by Qμ, a direct test of the alpha term's coupling. Okay, lab tests are crucial. Moving up in scale. Astrophysics. Gravitational waves. Definitely. The ring-down signal after 2 black holes merge, that's the final object settling down. We're getting amazing data now, like from GW250114.
And if the final object isn't a classical black hole, but one of these fractal black hole remnants,
its structure, defined by that fractal dimension DFA 1.8928, should subtly alter the space-time geometry right near its edge. This should imprint extra frequencies onto the ring-down signal, unique secondary quasi-normal modes. QNMs.
like extra notes in the black hole's chord.
Kind of, yeah. They'd be closely spaced and relatively weak, suppressed by that quantum constant gamma. Finding these specific fractal QNMs and high-quality gravitational wave signals would be compelling evidence for the BHRs. Not finding them, as sensitivity improves, would challenge the model. And finally, the biggest scales, cosmology. Testing that scale-dependent coupling alpha GA. This uses CMB lensing data from Planck and future surveys, combined with large-scale structure, LSS maps from Dīdāi, Euclid, LSST. We're looking at how matter clumps together over cosmic time.
Which Qμ says should be slightly suppressed at late times due to alpha K.
Right. We measure this via the growth function, often denoted as sigma 8. Qμ predicts a specific scale-dependent suppression in sigma 8 compared to standard lambda CDM, especially at lower redshifts.
And this suppression is the same effect that solves the Hubble tension.
It has to be consistent, yes. This predicted suppression also seems to resolve another nagging anomaly in the Planck data related to CMB lensing, the so-called Allen's tension. Seeing this specific pattern of growth suppression consistently across different cosmological probes would be powerful confirmation of the dynamic, entanglement-driven gravity.
It's a complex web of predictions. What if different tests give conflicting results? Say, gravitational waves suggest one value or behavior for alpha K, but LSS suggests another. Is there a plan for that?
There has to be. The validation program needs a built-in decision matrix. If, for example, high probes like GWs and Logan probes like LSS give inconsistent results for the coupling's scale dependence.
What do? Tweak the theory. You have defined options. Option 1, revise the functional form of alpha KZ. Maybe its dependence on redshift C's is more complicated than initially assumed, reflecting different eras of cosmic evolution. Option 2, rethink the underlying mechanism of entanglement saturation that dictates how the Qμ effect fades at large scales. But what's non-negotiable? What would actually break the theory fundamentally?
The absolute bedrock is causal structure. The theory posits that quantum information, specifically entanglement entropy gradients, causes changes in curvature. If future analyses, especially correlating LSS data with entropy proxies, show that the entanglement buildup doesn't consistently precede the gravitational changes.
If it's just correlation, not causation.
Then the core idea of emergent gravity fails. Entanglement-driving geometry is the fundamental premise. That causal link must be confirmed observationally.
Okay, so wrapping this up. The Qmn theory is putting forward a pretty radical solution to the Holy Grail problem.
It is. It argues gravity isn't fundamental in the old sense, but emerges from the thermodynamics and geometry of quantum entanglement. It unifies GR and QM by making spacetime itself an expression of a conserved underlying information network.
And its strength isn't just explaining away mysteries like the Hubble tension or dark matter or avoiding singularities, but deriving constants like alpha EM from a fundamental fractal geometry. It seems complete, consistent, and like you said, crucially falsifiable.
Exactly. It makes concrete predictions in the lab, in gravitational waves, in the cosmos.
It really paints a picture where the fabric of space-time isn't just a passive stage, but is actively shaped by the quantum information playing out within it.
That's the heart of it. And if experiments like LUXE find that unruh enhancement and the big surveys like Euclid confirm that specific scale-dependent growth suppression, well, it would strongly suggest the Holy Grail wasn't some static final equation, but the realization that cosmic geometry is quantum information made manifest.
Which leads to a pretty provocative final thought.
If the universe really does emerge from entanglement, from this deep interconnectedness, does that imply the geometry of the cosmos itself could have properties we usually associate with information systems, like memory or processing capacity? That's the next frontier this kind of thinking opens up.
A universe that computes itself into existence. Plenty to think about there. That's all the time we have for this deep dive. We'll see you next time.